Clinical chemistry, photometric assays. Spectrophotometry. So photometry by itself, or photometric instruments, measure light intensity. If we add spectro to it to make it spectrophotometry, spectro is the use of gratings to isolate a narrow range of wavelength. Radiant energy will be partially reflected, absorbed, and transmitted when passing through a substance. Planck's formula relates wavelength and energy. So E equals hv, E is energy, H is Planck's constant, and V is frequency. So how often a wave is detected. The shorter the wavelength, the higher the frequency. So if we have a detector here, and we have different wavelengths coming through. Here's a wave that's passing through. And then we're going to have a longer wavelength. We have wavelength as measured at the peaks. So this is one wavelength versus this being one wavelength. So shorter wavelengths are going to have a higher frequency as opposed to longer wavelengths. That peak is not going to be detected as frequent. A spectrophotometer is an instrument that measures absorption or emission of radiant energy to determine the concentration of atoms or molecules. For this, we have absorption and then we have emission. So for the absorption part, electromagnetic radiation is absorbed when it has the same frequency as a rotational or vibrational frequency in the atom or molecule it strikes. So this radiation, the electromagnetic radiation, is going through a substance, and it's going to come in contact with certain components of that substance. And if it has the same rotational or vibrational frequency as those components, it's going to be absorbed. When energy is absorbed, valence electrons are going to move up to a higher energy orbital. Eventually, those electrons are going to settle back down to ground state. So that's when we have emission. So it strikes a molecule, it vibrates at that same frequency, the energy gets absorbed, or the radiation gets absorbed, and it bumps that electron up, and then slowly the electron is going to come back down to ground state. Emitted electrons are going to emit that energy, fall down to the ground state, and they emit energy in the form of a characteristic wavelength. That creates spectra. Spectra of the sample are then compared to a database of spectra of known samples. This allows for the identification of substances within a sample. A basic spectrophotometer measures visible light between 400 to 800 nanometers. A UV visible spectrophotometer measures the UV component, which is about 100 to 400, plus the visible light component, which is 400 to 800, for a total of 100 to 800 nanometers. And this gives us a broader range of readings. Most instruments today record that it's about 190 to 900 nanometers. So anywhere within that range for a test question would be acceptable. Infrared spectrophotometers use the lower energy of the spectrum, and that's mostly to determine functional groups in molecules. The lower energy of the spectrum is 700 to 1000 nanometers. So recall that energy and wavelength are inversely related. The lower the energy, the longer the wavelength. So something that's got a shorter wavelength, like the one I drew before, has higher energy than something that has a longer wavelength. Think about someone jumping rope. So they go jump, 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 jump. That's a lot higher energy and a lot shorter wavelengths, as opposed to someone that goes jump, pause, jump, pause. So this is a much longer wavelength, lower energy. Beer's law states that the concentration of a substance is directly proportional to the amount of light that's absorbed, or inversely proportional to the logarithm of the light transmitted. So we look at absorption versus transmission. So here we see the percent transmittance, so it goes through the substance, and then you have this percent that's transmitted. If we have a blank, it's defined as 100% transmittance. So typically when we evaluate specimens, we're going to blank out the instrument, the spectrophotometer, and we want to blank it out with the same solvent that we use for measuring the other substances. So we're going to have something that doesn't have the substance that we're looking for, any interfering substances. It's just going to be the blank background solvent that we use. Then we have our sample. So when we have sample mixed in with that background, it's going to have a certain percentage of transmittance, because the sample itself is going to absorb some of that energy. So here's some calculations to know for your qualifying exam and for the upcoming test. So absorbance equals E times B times C. E is the absorptivity, that's the fraction of a specific wavelength of light absorbed by a given type of molecule. B is the length of the light path through the solution, and C is the concentration of absorbing molecules. Absorbance can also be calculated by the negative log of the transmittance. Additionally, if you're given the percent transmittance, absorbance can be calculated using the following. A equals 2 minus log percent T. Those three equations, again, are very important, not only for the upcoming test, but also for your qualifying exam. So you should make note of those and understand what they mean. A calibration curve. So when we're first trying to measure a substance, and we're looking for a very specific substance within a mixture of a sample, it's good to start out with a calibration curve. It helps us determine an unknown concentration of a substance. A calibration curve plots the absorbance at a specific wavelength versus the concentrations of standards of known concentration. These standards of known concentration can either be prepared using a serial dilution, or we can purchase standards. But basically we're going to create this curve and measure the absorbance, and then we can get this linear calibration curve. Then we can take an unknown substance, and if that unknown substance has, let's say we get an absorption of 0.5, we can estimate the concentration of that substance based on this calibration curve. So we know that this one had this concentration and it had this absorbance, and we know this one had this concentration and this absorbance. So if we know these, and these are set standards, and we know the concentration and we know the absorbance, we can estimate absorbance given, or estimate concentration given an absorbance. So we're going to put an unknown specimen into the spectrophotometer. We're going to do a reading, and let's say our reading comes back at 0.5. So we're going to take that reading of 0.5, we can come to the calibration curve and go over to where it crosses and then go down, and that will give us an estimated concentration. So probably about 57 or so ppm. The components of a spectrophotometer are listed out here. Now this is just a monochromator, very simple spectrophotometer. So we have a light source, and then there's an entrance slit, and then we have the monochromator, which has grating in it. There's an exit slit, then the light would go through the sample cuvette and into the PM tube, and then it gets detected by a detector, and then it's displayed. So the light, there's various light sources that exist based on the instrument. The monochromator allows for the isolation of individual wavelengths of light. The sample cuvette is a flat surface that allows for a constant light path. When angling the sample cuvette toward the light source, we want to make sure that that side is completely cleaned off. There's no outside debris on that, and it also has to be the flat surface. A typical cuvette usually has cloudy surfaces and flat surfaces, we want to make sure that the flat surface is exposed to that light path. The glass, it's inexpensive and it's used for visible light because they absorb light in the UV radiation, preventing transmittance. But quartz cuvettes are used to allow for transmission in the UV range. Quartz cuvettes are pretty expensive. They are definitely reusable. We would never just toss them out. But the quartz cuvette allows for the use in a UV vis spectrophotometer. The photodetector converts transmitted radiant energy to equivalent amounts of electrical energy. Photosensitive material gives off electrons when light energy strikes it. Electrons produce an electromotive force which can be measured. Spectrophotometer quality assurance. So wavelength accuracy. The wavelength indicated on the control is actually the wavelength being passed by the monochromator. This is checked using a standard of solutions. Stray light. Common causes are scratches on the optical surfaces or dust particles that allow light to reflect. It's measured using sharp cutoff filters that eliminate all radiation outside of the one of interest. And linearity. Use a carefully diluted set of colored solutions to produce a straight line calibration curve, and that can test linearity. Some considerations. Solvent absorption must be insignificant compared to solute absorption. So if the solvent, the substance that's supposed to be doing the diluting, that's the background material, if that's absorbing, that's an issue. So we need to only have like a very low amount of absorption in the solvent compared to the solute. Optical interferent is not present. So there shouldn't be any dust, debris, even like lipids. Sometimes if we have highly lipemic samples, those can cause optical interference. Chemical reactions do not occur between the molecule of interest and the solvent or other solutes in the solution. If the molecule of interest starts reacting with neighboring substances, it's not going to be able to be detected. There's other types of photometry. Atomic absorption spectrophotometer measures concentration by detecting absorption of atoms rather than molecules. It's extremely sensitive and it's used for the evaluation of trace metals, in other words, elements that are trace metals that could be found in biological specimens. Flame photometry measures light emitted by excited atoms. It's used to detect sodium, potassium, and lithium. However, this was replaced by ion selective electrodes. Fluorometry. It's used to measure concentrations of solutions containing fluorescent molecules, so it measures the fluorescence. It absorbs light at one wavelength and emits light of a lower energy. So in order for a molecule to fluoresce, it has to do that. It has to absorb light at one wavelength and emit light at a lower energy. There's a secondary filter in a fluorometer that allows only emission radiation to pass. This allows for the precise quantitation of biological molecules such as nucleic acids and proteins. There are some advantages over spectrophotometry. So fluorometry selects optimal wavelength for both absorption and fluorescence for increased specificity. So it not only measures absorption, it measures fluorescence, and that makes it a little bit more specific in detecting molecules. The emitted radiation is measured directly, so it's 1,000 times more sensitive. Chemiluminescence, part of chemical energy generated produces excited intermediates that decay to a ground state with emission of photons. Emitted radiation is measured with a photomultiplier, PM tube. There is no excitation radiation or monochromators that are required. It only involves the oxidation reactions of luminol, acridinium esters, and dioxetanes. Turbidity and nephelometry, means of measuring scattered light. Turbidity measures the concentration of particulate matter in a sample. Nephelometry is similar to turbidity, except it's a different angle of measurement. Lipemic specimens produce interfering background light intensity and excess scatter, so that's going to mess with these readings. Turbidity is also used in microbiology. So if we want to evaluate the number of organisms within a solution, we can grow up bacteria, and then we can see how turbid the solution is. We can also use turbidity measurements to dilute bacteria for certain assays. Laser applications. So laser stands for light amplification by stimulated emission of radiation. It's based on the interaction of radiant energy and suitably excited atoms or molecules. Light is polarized and coherent and has a narrow spectral width and small cross-sectional area with low divergence. It can serve as a source of incident energy in spectrometer or nephelometer applications. Laser spectrometry can be used for the determination of structure, identification of samples, and diagnosis.